In this video, we will be reviewing the exponential and logarithmic functions. We will begin by looking at the exponential. So the function defined by f of x equals b to the x, where b is greater than 0 and is not equal to 1, is called the exponential function. With base b. The domain is the set of all real numbers. So let's take a look at the graph of the exponential function. So we come over to Mathematica, manipulate, plot b to the x. Let's take x to go from minus 10 to 10. We're going to set the plot range to be 0 to 100. And then we're going to let b first vary from 2 to 10. So we're going to consider values of b larger than 1. And we go ahead and take a look. And let's play this and let's see what happens. So notice as b is getting larger, this is increasing much more rapidly, right? See that? But you should notice that it still has the same general shape, right? It's still very slow increase for values of x less than 0. The point where it's crossing the y-axis is not changing. The only thing that now changes is how quickly this is increasing. So if we pause it, we go down to 2, we can see that it has a slight incline and it gradually gets larger. If we now come over to b is 10, we can see that the steepness of the incline almost immediately increases. Okay, so what happens now? I'm going to take this, because I'm going to use the same kind of code. If we now set b to be less than 1, so let's say go from 1/10 to 1/2. But right away we can see a slight difference, right? It's almost a mirror image. But let's see what happens as b increases. So let's play this. You can see the reverse of what happened above is happening. Shape is still the same, right? What's changing though is this is moving farther and farther out. So we start the smallest value, 1/10, right? We can see, oh look, it's very slight increase down here. If I play it again, I want you to look that the point where it crosses the y-axis doesn't change. Right, go back. See, very, very steep incline here. If we now go to its smallest value of 1/2, we can see that there's still an incline and it's still getting larger, but it is at a much slower rate. We will now look at some properties of the exponential function. First, the domain is all real numbers. Second, the range is all positive real numbers. Second, the graph will always pass through the point 0, 1. It is continuous from -infinity to infinity. And as you noticed, it was increasing on -infinity to infinity for b greater than 1 and decreasing on -infinity to infinity if b was less than 1. Also, we look at laws of exponents. So we let a and b be positive numbers, and we let x and y be real numbers. Then the following are true. B to the x times b to the y is b to the x plus y. B to the x over b to the y is b to the x minus y. B to the x to the y is b to the x times y. A times b to the x is a to the x times b to the x. And a over b to the x is a to the x over b to the x. Okay. Now, these can all be proven fairly easily simply by using the fact that b to the x, remember, is b times b times b times so on and so forth times b x times. Now, while our base b can be any positive real number except for 1, there are two bases that are used the most. And they are the numbers 10 and e. We call base 10 the common base, and we call base e the natural base. Now, we can formally define the number e a little bit later, but for now, e is taken to be approximately 2.71828182845, right, so on and so forth. Let's now look at some examples for exponential functions. So this first example is going to be looking at using laws of exponents. So if we have 16 to the 7 over 4 times 16 to the negative 1 over 2, this is 16 to the 7/4 minus 1/2. Right, so this is then 16 to the 5 over 4. We can write 16 as 2 to the 4th. So this just becomes 2 to the 4 times 5 over 4, which is 2 to the 5th, which is 32. Next, if we look at 8 to the 5/3 over 8 to the negative 1/3, this is 8 to the 5/3 minus negative 1/3, which winds up being 8 squared, and that is 64. Now 64 to the 4/3 times negative 1/2. I'm sorry, raised to the negative 1/2. This is 64 to the 4 over 3 times negative 1 over 2, which is 64 to the negative 2/3. Now 64 is 4 cubed. So this becomes 4 to the 3 times negative 2/3, which is 4 to the minus 2. 4 to the minus 2 is 1 over 4 squared, and so this is 1 over 64. (16 times 81 to the negative quarter). We can write 16 as 2 to the 4th. We can write 81 as 3 to the 4th. Right, so we get 2 to the 4 times negative 1/4 times 3 to the 4 times negative 1/4. Right? So this winds up being 2 to the minus 1 times 3 to the minus 1. Which we can write as 2 times 3 to the minus 1, which is 6 to the minus 1, which is a sixth. And if we have 3 to the half divided by 2 to the half, all raised to the 4th, this winds up being 3 to the 4 over 2 divided by 2 to the 4 over 2, which is 3 squared over 2 squared. Oh, I'm sorry. I will leave it this way. I copied the example down wrong, but this is fine. This is 9 over 4. All right. Let's now look at solving an exponential equation, that is, an equation that involves an exponential function. So f of x is 2 to the 2x minus 1. We wish to find the value of x for which f of x is equal to 16. Well, that means that 2 to the 2x minus 1 is equal to 16. But keep in mind that 16 can be written as 2 to the 4th. Since we have the same base, the exponents would have to equal. And now this is just solving a linear equation. So 2x is equal to 5, which means that x itself is equal to 5/2. And now we turn our attention to logarithmic functions. Okay, now the function f of x equals this, which is read log base b of x, where again b has to be greater than 0 and not equal to 1, is called the logarithmic function base b. Now, log base b of x is equal to y if and only if x is equal b to the y. Right, so the logarithmic function is the inverse of the exponential function. And the domain is the set of all positive real numbers. So just like we did with the exponential, let's come over to Mathematica and examine the graphs of several logarithmic functions. So manipulate, plot, log base b of x. We'll let x go from 0 to 10. And plot range, let's say we'll go from minus 10 to 10. And we will let b range from 2 to 10 just like we did before. Okay, so again, let's notice what's happening. So it's maintaining the same general shape, right? Just like the exponential did. Point we're across the x-axis, notice, is never changing. What's changing is essentially this steepness here. If we now examine what happens for b less than 1, everything else is going to stay the same. I'm just going to change b to go from 1 over 10 to 1 over 2. And we will again notice what's happening. Notice once again, it is the same general shape. It's still crossing the x-axis at the exact same point. The only thing changing is essentially this steepness. Now let's look at some properties of the logarithmic function. Okay, so the domain is 0 to infinity. The range is all real numbers. Graph always passes through the point 1, 0. It is continuous over its domain. And it was increasing for b greater than 1 and decreasing for b less than 1. We also have laws of logarithms. So if m and n are positive numbers, and b is greater than 0, with b not equal to 1, then we have the following. Log base b of m times n is log base b of m plus log base b of n. Log base b of m over n is log base b of m minus log base b of n. Log base b of m to the n is equal to n times log base b of m. Log base b of 1 is equal to 0. And log base b of b is equal to 1. Now there's special notation used for the two common bases. For base 10, we simply write log of x. For base e, we write ln of x. And this is called the natural logarithm. And we close out this video with several examples using logarithmic functions. So this first example will be looking at the laws of logs. So if we had log base b of wx over yz, we could write this as log base b of wx minus log base b of yz, which could be written as log base b of w plus log base b of x minus the quantity of log base by plus log base b of z. Distributing that negative through, then we can write log base b of w plus log base b of x minus log base b of y minus log base b of z. If we had log base b of wx raised to the 3/5, we can write this as 3/5 times log base b of w times x, which would be 3/5 times the quantity log base bw plus log base bx. And then, of course, that 3/5 could distribute through, and we'd have 3/5 log base b of w plus 3/5 log base b of x. If we have e to the x ln of b, we can write this as e to the ln of b to the x. And that is just simply b to the x. And finally, natural log of x over the natural log of b is just log base b of x. This is the change of base formula. Okay, now finally let's look at this. We will solve log of x plus log of x plus 1 is equal to log of 6. So the first thing we want to do here is to combine the logs on the left-hand side and write that as x times x plus 1. That is equal to log of 6. Now we have same base, so what we're taking the logs of must be equal. distribute that x through. Now we want to subtract by 6. And now this is quadratic. What's on the left-hand side can be factored. Right, it factors to x minus 2 times x plus 3 is equal to 0. And so we have either x is 2 or x is negative 3. However, x equals negative 3 is not in the domain of log of x. So we discard it as a solution. So our only solution is 2. So that concludes this video on the exponential and logarithmic functions. In the next video, we will look at something brand new, and that is the idea of a limit of a function, as well as formally defining what we mean by saying a function is continuous.